All right, today we are going to have one of our mountaintop experiences in calculus. We are going to try to derive Kepler's laws from Newton's laws, at least according to the way our book did it. Probably not the way Newton did it. This is the way John Rogowski's calculus book does it, second edition. It was very appropriate this morning, though, when I was coming to school very early. I got up at 5 o'clock this morning because I was so focused on trying to prep for class and make this all work well. But it was great, and I would encourage you to get up early tomorrow because the night sky was absolutely gorgeous, and it was a really cold day this morning. Today is October 16th, 2015 in Minnesota, and it was a really cold morning, but the sky was perfectly clear. Right around 6 a.m. I was getting ready to come, and I got out, and I came to school. But when I went out and outside at first, I did see the night sky, and Venus, for example, was just amazing. This picture that you see here that I got online was accurate about 1 week ago, looking east about 1 hour before sunrise. Today is October 16th, so you don't see the moon anymore. Actually, Mercury, I believe, has gone below the horizon as well. I didn't see that. I didn't notice Regulus, but that's a star. I did notice Venus, Mars, and Jupiter. Mars was, as of today, a little bit to the left of Jupiter in the sky. And it is harder to see. Venus is super duper bright. That's the most beautiful part. It's just amazingly bright at about 6 o'clock in the morning. You should go out and see it. I mean, you can go back to bed tomorrow after you go out and see it. But set your alarm for 6, go out and see Venus. I think it's going to be clear tomorrow as well. Watch the news tonight just in case. Jupiter's pretty bright as well, though much further away. Mars was not real bright. It is slightly reddish. Again, now it is to the left of Jupiter, right about here in the night sky, because Mars moves faster through the night sky than Jupiter does, because it's closer. Okay? And it's going around the sun faster. I also found a website, The Planets Today, that shows the relative positions of these things in their orbits. However, you've got to be careful how you interpret this. This graph that's going to be shown is very much not to scale, okay? All right? The outer planets, especially Jupiter, Saturn, etc., are much, much further away than what this picture is showing. Which initially kind of goofed me up because I was thinking about Mars and Jupiter. And this is evidently the positions of the planets with respect to their positions in their orbits at the given moment in time. And in this picture, it looks like Mars should be to the right of Jupiter. But then I remembered, oh, this picture is not to scale. Jupiter is so much further away that it does appear that Mars in the night sky, or the early morning sky, is to the left of Jupiter. Okay? Even though in its position as far as the orbit goes, evidently Jupiter is closer to this line, right there. So that's kind of cool too. Okay, so yeah. I know it's Saturday, but you can go back to bed. Get up early and enjoy it. Venus is just so bright right now. It's amazing. So we're having our mountaintop calculus experience, deriving Kepler's laws from Newton's laws and from tools of calculus. Again, based on the derivations in the text, Multivariable Calculus by John Rogowski. Here are Kepler's 3 laws. We've seen these before. Let's think about them in more depth. I'm going to go through a lot of content here, fairly fast. I hope you can focus and enjoy it. Probably you're not going to want to take notes because it's probably just too much, but just really focus and think as well as you can. Try to follow it as well as you can. Kepler's first law is called the law of the ellipses. We know that. That says the orbit of a planet, or any other body like a comet, is an ellipse with the sun at one focus. Here's a picture of it that I found on the internet. This is greatly exaggerated for the Earth. The Earth's orbit is not nearly so elliptical. It's not nearly so eccentric. Some comets have orbits that might look similar to this. We've got an ellipse, planet or comet. There's the center of the ellipse. There's one of the foci, and the sun is supposed to be at one of the foci. Kepler's first law says the orbit is an ellipse with the sun at one focus. And you can see our other quantities involved here. A is the semi-major axis. It's the distance between the center of the ellipse and the vertices of the ellipse that are further away from the center. this point and this point. This point for the orbit is closest to the sun, that's called perihelion. This point over here is furthest from the sun, that's called aphelion. You also see the eccentricity coming into play. We know that the eccentricity by definition for us was c divided by a, where c was the distance between the center and either foci, either focus. E was c divided by a, and therefore c is e times a. So this distance is the eccentricity times the semi-major axis right there. RA is the distance between the sun and the aphelion position, and RP is the distance between the sun and the perihelion position. These equations are not too hard to derive. You can use the fact that RA plus RP is going to be 2 times A, 2 times the semi-major axis. That's one thing you can use to derive that, both of these equations actually. So there's the first law with more detail. What's the second law? Kepler's second law, law of equal areas in equal times, says the position vector sweeps out equal areas in equal times, which does have the net effect of making a planet or a comet move faster when it's closer to the sun at perihelion and slower when it's further away at aphelion. This is again greatly exaggerated. This orb here is made to look like the Earth. That is more exaggerated than the Earth's actual orbit. But one thing is accurate here. Perihelion, closest approach to the sun, actually does occur in early January. And aphelion, furthest, is in early July. Which makes people scratch their head and say, well, how can that be since January is cold and July is warm, at least in the northern hemisphere?
It's the curve that does the season.
Yeah, it's the tilt of the Earth that does the seasons, not the distance to the sun. The tilt of the Earth affects how direct the sun's rays are. In the summer, they're more direct. The sun is higher in the sky. It has less atmosphere to go through to get to the ground. In the winter, the tilt of the Earth makes the sun lower in the sky, and it has more atmosphere to go through to get to the ground. It's a lower angle, and so it's less heating. You know, think of it in the extremes. At the poles, you have complete nighttime in the winter, so you're getting no solar benefit there. And in the summer, it's always in the sky. So if you think of those in extremes, it helps you understand the seasons. So the seasons are not related to the distance. The distance has a very small effect on the amount of heat the Earth gets from the sun because of the fact that, well, the change in distance is so small. The eccentricity is not very big. The orbit looks like a circle even though it is a slight positive eccentricity. So these areas that you see here are supposed to be areas swept out in 1 month intervals, and they're supposed to all be equal to each other. So if it's going to sweep out this bigger area when it's close to the sun, it's going to have to move faster. I shouldn't have said bigger area. If it's going to sweep out this area in 1 month, it's going to have to move faster because it's a bigger angle. If it's going to sweep out this area in 1 month, it's going to have to move slower because it's a smaller angle. And Kepler's third law is more complicated. If t is the period of the orbit, not the rotation of the planet, the period of the orbit, how long it takes to go around the sun, and a is the semi-major axis of the orbit, then it turns out that the square of the period is proportional to the cube of the semi-major axis. Kepler did not figure out the constant proportionality, because Kepler didn't even know about big G, for example, the universal gravitation constant. It took Newton to figure out, amazingly, that the constant of proportionality is 4 pi squared over G times m, where again G is his universal gravitation constant, and m is the mass of the sun. That's pretty astonishing. Who would ever imagine that the constant of proportionality would be of that form? Okay? Here's the value of capital G in standard units, and the mass of the sun in kilograms standard units is this, approximately. Okay, now we want to go through and derive these laws. We'll start with Kepler's second law, because that's the easiest to derive. The equal areas swept out at equal times. The second easiest to derive, if we go by the order of this, at least, is the first law, that it's an ellipse. And the hardest one, although it's actually when you do all the spade work before, the third one is not necessarily the hardest one, but it's in order, it's the third one we're doing. So Kepler's second law, again, that's the equal areas in equal times. We make some assumptions similar to things we assumed for talking about the project. Assume we just got one planet of mass little m. You could pretend it's the Earth, you could pretend it's a comet, you could pretend it's Mars, whatever you want. And the sun is mass capital M. We're going to ignore the gravitational effects of all the other planets, all the other stars in the galaxy of the universe. Theoretically, they all do attract each other by gravity, but you might imagine them, so their effects sort of canceling each other out because they're so much further away and or so much less massive. So we ignore them and we get pretty good approximations, okay? And we get to be able to derive Kepler's law. So we're pretending the planet doesn't exert a force of gravity on the sun, even though it does. It's relatively small, so we're going to keep the sun fixed at the origin of our coordinate system. We're going to let, as usual, r be the position vector of the planet, which does depend on time because the planet moves. Let little r, or a non-bold-faced r, be its magnitude. So boldface represents the vector, lack of boldface represents the magnitude, or scalar, the length of the vector. We are going to find it convenient to define a unit vector to be E sub r. That's a unit vector, vector of length 1 in the direction of r. So in a picture on the board, got the sun here. We are going to imagine, for simplifying purposes, that our planet or comet or whatever starts on the horizontal axis. You can always choose your axes, rotate them if you need to make that happen. And we are actually ultimately going to assume, maybe not at the start, we're ultimately going to assume that the initial velocity vector does point straight up with respect to that picture. And the motion is counterclockwise. Those are assumptions we are going to make, and they can be justified by saying we can rotate our coordinate axes so that that happens, and we can think about a particular moment in time when the velocity vector at time 0 does happen to be perpendicular to the position vector. So the position vector is going to look like this at time 0, and the velocity vector is going to look like that. That will be a right angle, which does not necessarily mean we've seen that the orbit is a circle. It could be an ellipse with positive eccentricity. It depends on what the velocity vector happens to be, how long it is. This again is all stuff we've talked about before. Newton's law of universal gravitation, which many people think of as being his most amazing discovery. Even more so than other things in physics like F equals ma and calculus even. Okay, though we're using plenty of calculus here, is to realize that that force that causes you to stay on the ground, even when you jump, causes an apple to fall to the ground. The apocryphal story being he's sitting on the ground and it hits him in the head or whatever. The realization that that force of gravity, which everybody knew about going way back thousands and thousands of years, that is also what causes the planets to go in their orbits, what causes the moon to go around the Earth. That force of gravity is the same force. Newton imagined the moon in its motion sort of being in a continual fall toward the Earth. Now it doesn't fall toward the Earth because it's got some velocity that keeps it in an elliptical orbit around the Earth, but he sort of imagined it falling. And evidently, I don't know what kind of imagination caused him to realize that it was this equation, that the magnitude of the force is proportional to the mass of the sun and the mass of the Earth here when we're talking about the sun and the Earth, or the sun and sun planet, and inversely proportional to the square of the distance between them. I have no idea his thought process that allowed him to imagine that that would be true. Capital G is just the name of the proportionality constant. To find its numerical value in standard units, you have to do experiments. And again, this is a good approximation to it. It's an inverse square law because we're dividing by r squared there. The force itself, however, is a vector, and we need to take the opposite of the vector, which is the scalar f times this unit vector er, so that it points from the Earth or the other planet to the sun. Er itself points from the middle of the sun toward the planet, so you've got to multiply it by negative sign, -1, to make it go the opposite direction. Then we scale it up by a factor of scalar f. And you imagine as being positioned at the planet, at the center of the planet. That's the best way to imagine it. This makes it look like it's an inverse cube law, but no, it's an inverse square law. We've seen this before. I can enter these numerical values into Mathematica, and in the book, there's a shorthand for the value of capital G times the mass of the sun. The book calls that K. What is the value of K? That comes out to be about 1.32726 times 10 to the 20th. What would the units for K be? I guess if you multiply the units of G times the units for the mass of the sun, which are not written here but would be kilograms, the kilograms would cancel. I guess the units for this thing would be meters cubed times seconds to the negative 2. But you don't have to worry about what that means. You do have to use Newton's second law to get ultimately a differential equation. F equals ma. You replace the force with the particular force that is working here, the force of gravity. That's the force on the planet exerted by the sun. The little m's cancel the mass of the planet. Doesn't matter. You get this as your final differential equation. The second derivative of the position vector, the acceleration vector, does equal negative k, where k was capital G times capital M being the mass of the sun, divided by little r squared, non-vector r, the magnitude of the position vector squared. Negative sign there, and there's your unit vector, er, which is r divided by its magnitude. That's the key differential equation. We can get Mathematica to solve this differential equation numerically with ND-solve, as we've done already. And this code also allows me to change the initial velocity in the vertical direction. I call it v here. To experiment with that, I actually could have done this next bit of code more efficiently, I realized later, but it works. This next bit of code will generate a picture of the orbit of the planet around the sun, making the planet blue, pretending it's Earth, and making the sun yellow. We see the blue vector, which is sort of hidden by the green one a bit, to be the position vector of the planet. The red vector being its velocity vector, and the green vector being its acceleration vector. And that acceleration vector does point directly from the center of the planet toward the center of the sun. Actually, the red and green vectors are not the true velocity and acceleration vectors. I scaled them up to be much longer than they are actually in this picture. How much did I scale them? By quite a bit, you will see here. If we go up to this code, I scaled the velocity vector up by 10 million to get it to show up nicely in the picture. And I scaled the acceleration vector up by, what is that? 100 trillion, it looks like. Is how much I scaled the acceleration vector up by to get it to show up nicely in the picture. So those are definitely scaled up versions. I can change the initial velocity, and that does affect the eccentricity. If I make the initial velocity higher, it becomes eccentric, and the perihelion is on the right and the aphelion is on the left. If I make the initial velocity smaller in the vertical direction, it becomes an ellipse like that, where the perihelion is now on the left and the aphelion is on the right. Those elliptical orbits are more interesting, you might say, especially when you focus on the velocity vector, because it shows how it changes length more clearly.
You pulled it back, essentially, by choosing velocity.
Yeah, I made this velocity, initial velocity, higher, which makes it go further this way initially. You can see that velocity vector, or the red vector, changing size a bit. It is longer over here and it's shorter over there. It's speeding up over here and slowing down over there. All right, this code does the same. Okay, this code down here does the same thing, but in 3 dimensions. Make a 3-dimensional picture, and I also added another vector that I'll talk about in a minute here. So here's a 3-dimensional picture of it. Let's make it eccentric. Slow it down a bit. There's a 3-dimensional picture, but the orbit is in a plane. What is that other vector that's pointing upward? Essentially, it's proportional to the angular momentum vector. It's formed with a cross product of the position vector and the velocity vector, as we will see. It's not equal to the angular momentum vector, but it's proportional to it. If you know about angular momentum vectors. This code right here, below this, oops, get rid of that. Below this animation, you see some formulas, essentially, some expressions. 4 pi squared over k, and that thing times a cubed and t squared. What I'd like to do briefly here is try to numerically confirm approximately that Kepler's third law works before I go on. If you look at a particular orbit of a particular body, planet, and A is its semi-major axis and capital T is its period, these quantities, according to Kepler's third law, should be equal to each other. Again, here was the statement of Kepler's third law up here, this equation. G times m is the k, so I've got a k instead of g times m down here, right there. If I look at this orbit and try to estimate A and capital T from this picture, hopefully I will get numerical values that are fairly close to each other here. How can I estimate A and capital T from the picture? Well, I only want one period of the orbit. It goes around once here. It looks like capital T is close to 10 to the 8th. Can you see that up there? This number here. And what is the semi-major axis here? I think the center of the ellipse is right around there. That'll be about negative 1.75 times 10 to the 11th. So the semi-major axis would be this distance, about 1.75 times 10 to the 11th plus 1.5 times 10 to the 11th. That would be 3.25 times 10 to the 11th, approximately, for the semi-major axis. So let's try replacing A with 3.25 times 10 to the 11th. This is not exactly right, I'm sure. Well, what do we get? We get about that. Let's try replacing T with, should we try 10 to the 8th, or should we try 1.04 times 10 to the 8th? I'm not sure. We'll try them both. 10 to the 8th. This is Mathematica's notation that allows us to substitute into those formulas. Yeah, they're both about 10 to the 16th. Let's try 1.04. Okay, it's not exactly 1.04, maybe 1.02 or something. Closer, 1.01. They're pretty close, okay? Ballpark estimates. This helps you believe the third law. If I switched the eccentricity by changing the initial upward velocity, it should still work, okay? I won't take the time to do that. Turns out a key fact in all these derivations that I'm about to get into now, a bit more theoretical here, a key fact is that this vector, r cross v, the position vector cross the velocity vector, is constant. And this turns out to be a key fact in a lot of these derivations of these laws. How do you derive that fact itself? It's right here. By the product rule for cross products, if we differentiate both sides of this equation with respect to time, you take the derivative of the first thing, cross the second, the derivative of r is v, add the first thing times the derivative of the second, r cross a. Now v cross v is 0, the 0 vector, right? We know that. It's a property of cross products. You cross a vector with itself, you get the 0. Actually, you cross any vector with any multiple of itself, you get 0. So this term goes away. V cross v is 0. But also, because of the differential equation, we know the acceleration vector is parallel to, but the opposite direction as the position vector. So we can replace A with that thing, and we can factor out the negative k over r cubed, and use the fact that r cross r is the 0 vector to say this derivative is the 0 vector, and therefore j is constant in time. That turns out to be a real key fact for deriving a lot of Kepler's laws. Did Newton know it? Probably, I would imagine so. This is probably a pretty fundamental thing that he knew. probably made use of, though again, if you try to read Newton's writings, it's notoriously difficult, okay, because he's using sort of Old English style, and there's not many standard kinds of equations in the way we write them today. So it's notoriously difficult to read Newton's writings to understand Newton, but I'm imagining that's probably something that he...
Didn't he also like put like a dot over his? Like,
Yeah, he used dots for derivatives, right, with respect to time. Here's a three-dimensional picture. Yeah, this magenta-colored vector here, that is J, or a scaled-up version of J. In this code, actually it's a scaled-down version. In this code, I used a cross product, and it looks like I scaled J down by, what would this be? That's 0.0001 tenth, 100,000, 1/10,000ths, as long as it actually is. I made it shorter so that I can see it. That's J. J does change in size if you change the initial velocity. But once you pick an initial velocity, then J stays a constant length and always points upward because it's a cross product of R and V. And you can see for that given orbit, J is staying constant. If I picked a different V, then I get a different J. J is different for different planets, which should make sense. But for any given planet, it stays constant. Does its magnitude stay constant? I couldn't get Mathematica to plot this. It was giving me errors, but I did get it to calculate the magnitude of J for a couple different times, and we see we get the same magnitude those two different times. I wasn't sure why it wasn't plotting it. I couldn't figure out my error in trying to get it to plot. Anyway, the fact that J is constant is enough to show the motion of the planet is in a plane. J is constant and it's perpendicular, orthogonal to R and V all the time. It's always pointing in the same direction. R and V always have to be in the same plane. So the planet's got to stay in a plane, which makes good intuitive sense. Does it sweep out equal areas and equal times? We know the formula for area swept out of a polar curve is given by that equation. We can relate it to time because theta does depend on time, and maybe it'd be nice to use a different function name for theta, like I can call it beta of t, to ultimately get the areas depending on time. We can also use the chain rule to differentiate A with respect to time, and if you do that, you get this quantity, because of the fundamental theorem of calculus, the derivative of A, the area swept out with respect to the angle, is this. The integral sign and the derivative essentially cancel. This function is an antiderivative of its derivative, is another way to think of that, which will be, again, 1/2 times the integrand here. You can use that along with d theta dt, which I'm writing as theta prime. Whenever I use a prime, it's going to be a derivative with respect to t. If I do a derivative with respect to theta, I will typically try to use the Leibniz notation. That's what the book does. You know, everything depends on time, but you can, because the planet is moving and the angle's changing, you can think of it as everything is depending on theta too. And theta depends on time, and time depends on theta. They're all related to each other, all these variables. It turns out that this quantity is equal to this all the time, and that is a constant, because we already saw that dj dt was 0. Here's an intuitive derivation of relating the derivative of the area swept out with respect to time and J, where J again is a constant. If you draw a picture of a small motion of the planet over a small interval of time, now the orbit is an ellipse, and so technically speaking this is a curve there, and so this is not a triangle. However, if the time interval is small, it's going to be well approximated by a triangle. That's almost straight right there. And we know from a fact about cross products that the cross product of two vectors, I hope you remember this, does equal the area of the parallelogram that they span. That was a graded problem actually to do that in 2 dimensions. And therefore, half the cross product magnitude, I'm talking about the magnitude of the cross product, I should say. Half of the magnitude of the cross product is equal to half the area. It's equal to the area of this triangle. And that's approximately what we're seeing here. Again, it's not exactly a triangle, but approximately a triangle. So because of that, the change in area, that area of this thing here, that's approximately a triangle, is well approximated by half the magnitude of this cross product. R of t is the initial position vector. This difference right there is actually, that difference is actually this vector here. But the area will equal the magnitude of that cross product. It's a little strange because it would also equal the magnitude of this cross with that. But the angles are different, so it probably works out. I haven't checked it. So in the limit as delta t goes to 0, it makes some intuitive sense that we should get 1/2 of j, where j again is defined to be the length of this cross product, which is constant. It's an intuitive derivation. It's not rigorous because this approximation is not rigorous. You know, what does approximately equal to really mean? It's just an intuitive approach. Here's a more rigorous definition. This is where it starts to get difficult to follow here. Let's go ahead and try to make some sense of this. You've got two vectors here, ER and E theta, that we're saying both depend on the angle theta of the planet as it moves. Come back to this picture. Of course, R is really, really long, and ER is really, really short, 1 meter long, so to speak, in the center of the Earth. Okay, it's like this long in the center of the Earth. ER is way in there. It does depend on the angle here. By trigonometry, its first component would be cos theta, and its second component would be sine theta, and that is unit length. It's going to change as the planet moves. It's going to rotate. It'll always stay a unit length, but it'll rotate. As time goes by, theta changes, so this changes. It does depend on t ultimately. I can also write another vector by sort of doing the similar trick as we used with two-dimensional osculating circles. By switching these components around and putting a negative sign in front of one of them, we get a vector that's orthogonal to the given vector. We're not worried about osculating circles here, so we're not worried about what's the direction of the center of curvature. So it's standard to put a negative sign in front of this one, and in a picture, if if ER looks like this, E theta will look like this. And this will be a right angle. Just a trick for creating a vector that's orthogonal to the given one. It's still a unit vector. ER and E theta both change as time goes by. They both rotate counterclockwise if the planet is going counterclockwise. Turns out their derivatives with respect to theta are also related. Double the screen here. For example, the derivative of ER with respect to theta is E theta. E theta measures the rate of change